In this tutorial, we're going to talk about the law of mass action, also known as mass action kinetics. Mass action kinetics is a fundamental theory for deterministic models, for the creation of deterministic models, and it's based off of the assumption that rates of reactions are directly proportional to the concentration of the reactants. So that's to say, for example, if we had A goes to C, A goes to C. For example, a very simple reaction: A just becomes C, reacts to become C in a beaker, say, and we have concentration of A is 10, for example, and the rate of reaction, which would be how much of C is being created per second, the rate of reaction was 2 molar per second. Then if we doubled the concentration of A, so this is at a given point in time, let's just write that out, at say t equals 0. If we doubled the concentration of A, we would double the rate of reaction at that given time as well. Or in other words, dc by dt is directly proportional to A. So this is the most simple example. A goes to C. There'll also be a coefficient of proportionality, which will be found empirically, which we might call K here. So in this example, it would be 0.2, because when A is 10, when the concentration of A is 10 molars, the rate of reaction is 2. And so if we write that out over here, 2 is equal to K times 10. So K equals 2 over 10, which equals 0.2. So all in all, our rate equation here would be dc by dt, concentration of C over time, is equal to 0.2 times the concentration of A. And this would be for any time. So here we took a specific time at t equals 0, for example, in this example, and we found that concentration of A was 10, the rate was 2, and so we could find K from that over here. We found K was 0.2, and now we can apply this to any time. We can also write the rate equation for A. In other words, how much of A is used up. Because A is being used up as time passes, it will simply be the negative of the C rate equation. So these are our two rate equations for our simple system, or our total ODEs, ordinary differential equations. Both of these are ordinary, as we discussed in the first tutorial, because they are both dependent on only one, because all variables are dependent on time. C is dependent on time, and A is dependent on time as well. Consider now adding in the reverse reaction. So a second example, A goes to C, but also C can go back to A. So in this case we have effectively two reactions. A goes to C, and C goes to A. So we're going to define the coefficient of proportionality as K forward, K subscript F, K reverse, K subscript R, or up here KF, KR, like so. Now we can use the exact same model we produced in the first example and combine the two. So for the first reaction, A goes to C, we'll have the total ODEs dA by dt equals minus k forward, kf, times a, and likewise dc by dt is positive kf multiplied by a. In the forward reaction, a is being used up, so it's negative. In the reverse reaction, c is being produced, so it's positive. And for the second reaction, this one here, we have c goes to a with kr as the coefficient of proportionality. And so we have dc, or let's go with dA by dt equals, well, it's being produced here with the coefficient of proportionality being kr and the reactant being c. So we have plus kr times the concentration of c. And the second differential equation for the second reaction is dc by dt, the concentration of c, rate equation for c, sorry. Well, c is being used up now, so it's going to be minus, and again the coefficient of proportionality is kr, k reverse, so we have minus kr times c. So these are our four differential equations. 1, 2, 3, 4. These first two here for the first reaction here, and these two, for the second reaction here. But we can combine these together. So here we have the rate of reaction for A. Again, we have dA by dt. And this is just for the forward, and this is just for the reverse. So we can combine these two. And likewise, we can combine these two to have the total ODEs dA by dt equals, so we have minus k forward times A plus k reverse, times C, and for the concentration of C rate equation, ODE, we have plus KFA minus KRC. So again, just to reiterate, this equation is only for the forward reaction, and this is only for the reverse, so the combined is the total ODE for A. So this is, just forward, this is just reverse, and likewise for C, this is just the forward and just the reverse. So we combine the two, we add them, and we get these total ODEs for A and for C. And you'll notice that they are identical if we just change the signs to minus here and plus here, put that in a bracket and subtract. You see they're identical, but the signs are reversed. And that's because, as we saw in the first example, as A is used up, C is produced, and likewise as C is used up, A is produced. And so there is a symmetry to the total ODEs. Next, we're going to introduce another reactant, an additional reactant, to add complexity. A plus B goes to C, and we're still going to have the reverse reaction. So we have A plus B goes to C, firstly, and secondly, we have C goes to A plus B. And again, we're going to use the same nomenclature and say Kf is the coefficient of proportionality for the forward reaction, K forward, and likewise Kr for the reverse. In this example, we have two reactants reacting together to form a C, which indicates that, implies that the rate of reaction for C will be dependent on both the concentration of A and the concentration of B. So in the simplest example, if we have lots of A molecules but no B molecules, we can't produce any C because we need the B molecules to react to make the C molecule in effect. So we see that it must be dependent on both A and B in the same term. So we write this as dc by dt equals plus, because it's being produced in the reaction, Kf for the forward, concentration of A multiplied by the concentration of B. So we multiply them together. So we see that if B equals 0, concentration of B equals 0, then the rate equals 0 as well. So in this way, it's consistent. So going back to the reaction equations, we can do the same steps as we did previously and form three total ODEs for A, B, and C. Now we can see that, again, there'll be a symmetry between A and B and C, because A and B are producing C is producing A and B, as we did before. But there'll also be a similarity between A and B, or in fact, they'll be identical. The total ODEs for A and for B will be identical. And we're going to show this now quickly. So dc by dt, we have dB by dt, and we have dA by dt. We have three reactants, or three products, and so we have three total ODEs. dc by dt is Kf A B, and we see here that it also reacts, C also reacts to become A plus B, so the C will react, and therefore it will be negative, because we're talking about the C ODE, minus K reverse, Kr times C, because the reverse reaction is only dependent on C. For B, on the other hand, B is used up in this reaction, so we'll have minus K forward, and the reaction rate will be dependent on A and B, concentration of A and B. And likewise in this reaction, C is being used up, C as the reactant, B is being produced, so it will be plus K reverse times C. And we see here as well for A. A is being used up to produce C with the coefficient of proportionality K forward, Kf. So minus Kf A times B. And for the reverse reaction, C is the reactant, C is being used up. So therefore A is being produced in this reaction with a coefficient of proportionality K reverse. So we have plus KRC. So we can again see the symmetry between C and A and B, and we also see that A and B are identical in this particular reaction. Next, we're going to consider reaction coefficients. So consider 2A goes to C. So there now is no longer the one-to-one nature. The stoichiometric coefficients are now different. Well, we can look at it in a different way, of A plus A goes to C. So now it looks very similar to our previous reaction equation, A plus B goes to C, but we have two A's reacting together to make C. So we've already produced these, the total ODEs, we've already worked those out. So let's write them out. So the total ODEs, dc by dt equals, again we're going to have K forward and K reverse, K forward, K reverse, and again A plus A goes to C, it's the K forward, C goes to A plus A is the reverse. So for C we have A's being used up to produce C in the forward reaction, so we have plus K forward A. So now looking back at this equation here, or our total ODEs before, we had Kf times A times B, the concentration of A times the concentration of B. So we'll do the same here, concentration of A times the concentration of A this time, because it's A plus A. But we see that this is just A times A, or A squared. So just to finish out this total ODE, Kr times the concentration of C, so the reverse reaction is being used up, so it's minus, and C is the reactant. But we can rewrite this as K forward times the concentration of A squared minus Kr times C. So we see here that the stoichiometric coefficient for the forward reaction for A was 2, and in the rate equation, the concentration of A was then put to a power of 2. And we saw this because A plus A means we have, in the reaction equation, in the rate equation, sorry, we have Kf times A. These combine together to make A squared. And we can continue this arbitrarily. If we had 3A, it would be A plus A. Then we'd have Kf times A, and then we'd have A cubed. So what we can say, in general, is that the stoichiometric coefficient of a reactant will translate to the power that reactant is put to in the rate equation. So that means our total ODEs altogether is dC by dt. So we have 2A, so K forward plus K forward, A squared minus K reverse C, again, as we have before. And likewise for A, concentration of A equals minus K forward, because it's being used up now, A squared plus K reverse C. C is the reactant, it's being produced, and Kr is the coefficient of proportionality. Now note here that A here isn't put to any power, because this is simply describing the rate of reaction for A, not the rate of reaction for A squared. So it's only in the ODE itself, over here, where we describe the rate using mass action kinetics, that there is a power. Finally, we're going to look at one last example, and that is degradation. Degradation is a fairly simple instance of mass action kinetics. We have A, some substance A that's useful goes to a null object, some other substance that is not useful. We don't really care what it is. It doesn't affect the system we care about, and so modeling the product or products that are produced is fairly redundant. There's no purpose in modeling it, and there is no reverse reaction either. And so in this case, we can simply write dA by dt as we have done before. We instead of using K, we use delta for degradation in general. This is the nomenclature that's used, delta. So you have dA by dt, the rate equation for A, is minus, because it's a reactant, it's being used up, and we're doing the A rate equation, minus delta times the concentration of A. Now there's no reverse reaction, so there's no plus here. And we don't care about the rate equation for the products because, as I said, they're redundant. And so we simply have one differential equation, dA by dt equals minus delta times the concentration of A. That concludes this tutorial on mass action kinetics. We covered some very simple examples of mass action kinetics, covering a simple reaction, A goes to B. We also covered, C, sorry, we did C. We had the reverse reaction, A goes to C, but C can go back to A. We introduced a new reactant, A plus B goes to C, and we also introduced new stoichiometric coefficients that weren't equal to 1 with the reverse reaction, and finally we covered degradation as an example. And so from this tutorial, we were able to model all of these reactions using mass action kinetics. modeling it deterministically, and this is the basis for many deterministic models. And from here, more complexity can be added, but fundamentally, these are the basic ideas that all mass action kinetics models are based upon.